Hello class, welcome back. And today I'm going to be talking about chapter 7. And chapter 7 is just going over heat transfer and change of phase. Basically just continuing on from chapter 6 where we talked about basically heat and temperature. All right, so first I'm going to talk about the 3 kinds of heat transfer. So there's 3 kinds of heat transfer. The first one is conduction. The second one is convection. And the third one is radiation. So to put it simply, conduction is basically the transfer of heat through direct contact. Convection is the transfer of heat through a fluid of some sort. And radiation is the transfer of heat through electromagnetic waves, right? So that's basically what each one of those are kind of in a nutshell, but I'm going to go a little bit deeper into each one of those. So let's start with conduction. So as I just said, conduction is basically the transfer of thermal energy through direct contact. Boom. So some examples of conduction would be like, if you walk outside and you have no shoes or socks on, there would be basically conduction between your feet and the ground, right? Another example would be if you have a stove top, not a gas top, but a stove top, in your kitchen, and you put your, let's say you put your pot directly onto the stove hot, whatever liquid you have in that pot is going to heat up through conduction because it's in direct contact with the stove. If you hug somebody, that would be a form of heat transfer through conduction because you're in direct contact with that person. And the heat is always going to travel from hot to cold, right? I think I discussed that a little bit last time. So if it's really, really hot outside, the concrete is really, really hot, and you step outside, with no shoes, no socks, the heat from the concrete is going to go, the temperature from the concrete is basically going to travel from the concrete upwards towards your feet, making your feet really, really hot. If a person is really, really cold and another person's really, really hot, and the hot person hugs that cold person, then the heat's going to transfer from the hot person towards the cold person, right? So I think that makes pretty good sense, right? And I guess another thing about conduction that I want to bring up is insulation. And basically insulation just slows the rate of thermal energy flow. So insulation basically just slows the rate of thermal energy flow. So as far as heat transfer is concerned, we have things that are good conductors, and we have things that are bad conductors that we would call insulators. So an example of a good conductor would be like most metals. So like metals, would be a good conductor. So if you have like a stove top, usually your stove top is made out of some type of metal ring, right? And then that metal ring heats up. Then you put your stove on top of that. And so it's a metal ring because it's a good conductor. Or if you have a pan, right? Your pan is typically made out of metal. It's because metals are good conductors. Basically just meaning they heat up fairly easily. You know, versus an insulator, things that are insulators would be like wood, paper, coal. So insulators, that's not how you spell insulator. So insulators would be like paper, wood, coal. And basically these are things that don't heat up as well as metals do, right? So basically notice that I put coal on here. So coal is not a good conductor, it's more so of an insulator. And so basically that means you can heat up coal, and if you're in direct contact with coal, the heat won't transfer to you as well as if you were to heat up a metal. So that's why, you know, you see people walking on hot coals, because coal is not a good conductor or an insulator. So you can probably walk across coal a lot easier than you can walk across hot metal, because the hot metal is a really good conductor. So meaning that it's going to transfer that heat to you a lot faster than what coal would. All right. So now let's talk about what's the next one that I mentioned? Convection, right? So heat transfer through convection, and this is basically the transfer of thermal energy through motion of fluids. So when I say motion of fluids, you can just kind of think of air, because air is considered to be kind of like a fluid. And a good example of convection would be the oven. All right? Because the way the oven works is basically on the very bottom of the oven, you know, you have some type of metal that's being heated up, and then that metal basically is heating up the air inside of the oven, right? And then you put something inside of the oven, and then it's basically going to heat up due to the hot air that's inside the oven. So an oven would be a good example of convection. All right, so now I think that makes sense. And let's see, I'm looking at the slides here. Okay, so they also bring up something called cooling by expansion. All right, so I'm sure we've all heard the saying that hot air rises and cool air falls, right? So we've heard this saying, hot air rises, hot air rises, and cool air falls. All right, so if you have a house with a upstairs, and that same house also has a basement, if you go into that house, basically the upstairs is going to be a lot hotter than the basement, right? Because hot air is going to tend to rise towards the top level of the house, while the cold air is going to fall towards the bottom of the house or the basement. Basically, hot air rises because as you increase the temperature of air, so the air molecules are going to basically get more and more kinetic energy. And so they're going to be moving a lot faster. And so as hot air rises, it also tends to expand. Then so as it expands, so as hot air rises, it also expands. And then as it expands, it also becomes less dense. So it also becomes less dense. And so the fact that it's less dense is also another reason why hot air rises and cold air falls, right? So going back to, thinking about if you have some liquid, right? And this liquid has different things inside of it. Boom, like that. So whatever settles at the bottom of it is the most dense, right? So this is the most dense, and whatever is at the top is the least dense. And so you can kind of think of this scenario as the same as how air behaves. And so as air heats up, it's going to expand and become less dense. And so since it's less dense, it's going to raise up to the top, whereas cold air falls because it compresses and becomes more dense. Boom. Then also, as hot air tends to expand, it also cools down. So as that hot air also expands and rises, it's also going to cool down because it's more spread out. Okay. So now the last form of heat transfer I'm going to discuss is let's write it in blue. Radiation. Radiation. And radiation is basically just the transfer of heat, or the transfer of thermal energy. Transfer of thermal energy through electromagnetic waves. Boom. So a good example of radiation or heat transfer through radiation would be your microwave, right? So example would be like a microwave. So the way the microwave works is the microwave isn't necessarily, like if you turn on a microwave, turn it on for 3 minutes, you open it up. If you put your hand inside of the microwave, it's not actually hot inside the microwave, but whatever foods you have inside the microwave is hot. But the surrounding area of the microwave is not hot. So it's not heated up by convection nor conduction, but instead heated up through radiation using microwaves. So what the microwave does is it releases basically electromagnetic waves in the form of microwaves. And so those microwaves are released inside of the microwave. And then those waves basically make contact with the food or whatever you have inside the microwave. And then it adds energy to it. And then that energy that gets added to the food, basically heats it up. So that's essentially how a microwave works. There's a little bit more physics behind it, but we don't have to get into it that deep, because really what the microwave does, it actually resonates with the water molecules that's inside the food, and then basically flips the water molecules over and over, excites it, and then that's what's warming up the food. But, don't worry about all that. Long story short, the food is warmed up through radiation or microwaves. All right, so let me see here. All right, so another form of basically heat. Well, actually, let me say this. All objects basically radiate. All objects that have some temperature. All objects radiate. So all objects radiate. All objects that are above absolute zero radiate, but there are no objects that can actually reach absolute zero. So we can basically say all objects radiate because they have some form of heat. And they radiate basically in the form of infrared. Radiation. So infrared radiation is basically associated with your temperature or your heat. So people that have night vision goggles, you put on these night vision goggles, you can basically see people, but what you're seeing is that person's infrared radiation because they have some temperature associated with them. And so since all objects have some amount of temperature, all objects then hence have some form of infrared radiation. So we don't actually see, infrared radiation with our eyes like you can with night vision goggles or the way some animals can, say, I think snakes can actually see in the infrared spectrum. So they can actually see your body temperature. But instead of seeing infrared radiation, we can feel infrared radiation, in the form of temperature, right? So something that's hot is going to have a high infrared radiation, or we could say it has a high frequency. And so if it has a higher frequency, it has short waves. Something that's cold is going to have a lower frequency, but long waves. All right, and then there's a little kind of diagram or picture in the slides that looks something like this. So we have basically a girl holding a rope, and she's whipping it really, really fast. So the faster she whips it, the higher the frequency. You can kind of see that because there's a lot of arcs going up and down, right? So this would be like for an object that's hot, and kind of notice that the waves are shorter, right? Because the frequency is high. So the waves here are shorter versus, they have another picture of her whipping it way slower. So you can see here, this is a lower frequency because there's like a hump here, a hump way over here, indicating a lower frequency. And then just kind of look at the distance of the waves in between. They're way longer. So this would be like for a cold object, and this would be for a hot object. Boom. Okay, So I think that makes sense. And so some other things that also radiate are things like our sun. Obviously, our sun is constantly, radiating energy that is basically hitting our earth. So you can imagine basically this being the sun because the sun is very, very, very hot. And so it's radiating basically these high frequency waves. Make this the sun. And let's put the earth over here. But the earth also has some temperature associated with it, right? So the earth also has a temperature, but the temperature of the earth is nowhere near the temperature of the sun. So the earth actually radiates waves that are a bit longer, look kind of like that. But then also those waves get trapped in our atmosphere. So basically, the earth has radiation being absorbed from the sun. And then there's also the radiation that's trapped in our atmosphere due to they call it terrestrial radiation from the earth. And this is basically kind of like a greenhouse effect, which I'm going to discuss right after I talk about emitters and absorbers. So a moment ago, I just said all objects radiate, right? So since all objects radiate, all objects also absorb. So all objects absorb and radiate. So all objects absorb. How do you spell absorb? And emit. Actually, I'm gonna write this. All objects absorb. There we go. So all objects absorb and emit radiation. Boom. So all objects absorb and emit radiation, but some objects absorb and emit radiation better than others. And basically, this ability for an object to absorb and radiate thermal energy, because we're talking about thermal energy, is basically indicated by its color. So good absorbers then, so good absorbers are, also good emitters. Good absorbers, I'm saying, and emitters. And emitters are dark in color, whereas poor absorbers and emitters, or things that are more reflective, tend to be lighter in color. So let's say poor absorbers and emitters are lighter in color. Boom. So I think this kind of makes sense, right? Because if you were to, let's say you go outside and you try to look at a white piece of paper on a bright day, if you try to look at a white piece of paper on a bright day while you're outside, it may actually, strain your eye. It may actually hurt your eyes a little bit because this paper is white, so it's lighter in color. meaning that it's a poor absorber, also a poor emitter. Basically mean it's like very reflective. And so a lot of light is being reflected off of that white surface versus if you have a black piece of paper, so a darker color piece of paper, which is a good absorber, would be a lot easier on your eyes to look at on a bright day. Cool. So now that we kind of got this understanding of the way heat is transferred, through conduction, convection, and radiation. Now we could talk a little bit about, or just briefly about, Newton's law of cooling. Newton's law of cooling, which basically just says the temperature difference, right like this, the temp difference of an object with its surroundings determines the rate of cooling or heating. Boom. So Newton's law of cooling basically says the temperature difference, shorthand, temp difference, the temperature difference of an object with its surroundings determines the rate or how fast it heats up or cools down. So obviously, if I have a hot cup of coffee and I just have it sitting, on the counter, obviously it's going to cool down, right? Because the temperature or the heat from the coffee is going to go out into the atmosphere and try to match the temperature of the surrounding room. But it's probably going to take some time. It's going to be a while before that coffee really cools down. And that's because the temperature difference isn't that great between the coffee versus the surrounding air. Versus if I were to take that coffee and put it in the freezer. So if I get that hot coffee, put it in the freezer, it's basically a greater temperature difference. And so the rate of which it's going to cool is going to be a lot faster. So I think that kind of makes, logical sense. So that's Newton's law of cooling. Basically just the temperature difference of an object with its surrounding determines the rate of cooling or heating. Cool. So if you're looking at the slides now go over the greenhouse effect. I think you can probably read that on your own. It's a little self-explanatory. So I'm not actually going to talk too much about that part, but I'm going to get right into the phases of matter. So let's see, phases of matter. Must be two T's. Matter. Boom. So obviously, there's three phases of matter that we're going to be talking about. There's solid, which would be like ice if we're talking about water. Is liquid, which would be, water itself. And then there's gas, which would be water vapor or steam. And then there's also the fourth state of matter, which is plasma, which comes after gas, but, not in the scope of this class. So we're just going to be looking at these three, right? So solid, liquid, and gas, or ice, water, and water vapor. Cool. So if we have some ice and that ice is melting and it becomes a liquid, or the ice melts and becomes water, we call that fusion. So we call this fusion. When liquid or water becomes water vapor, we call that evaporation or vaporization. 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 Yeah, evaporation. Yeah, evaporation. I guess I spelled that extra. Actually, I had it right. And then actually we have when an object goes from solid, skips liquid and goes straight to a gas state, and that's called sublimation. Sublimation. So an example of sublimation would be like dry ice. You know, if you have dry ice, which is basically a solid, right? But if you have dry ice at room temperature, it's gonna go straight from solid to gas, which makes the steam, smoky effect around it. So that's what we call sublimation. And whenever something goes in this direction here, this is energy being absorbed. Being absorbed. Hope we don't read that. That's supposed to say absorbed. So going this way, this is energy being absorbed. Because to go from a solid to a liquid, you basically have to add heat to that object, right? Or add heat to this ice so that it melts and becomes liquid. Now, similarly, you have to add heat to liquid before it can become a gas. And so we can actually also go the other way. I'm going to use black. If we go from gas to a liquid, we call that condensation. Condensation. And then if we go from a liquid to a solid, we call that solidification. Solidification. Not sure if I spelled that right, but this is supposed to say solidification whenever you go from a liquid to a gas. And whenever you go in this direction, this is energy being released. Boom. So let me show you these phases of matter in a different way. So if I were to draw a chart here, we're down here on the x-axis is the heat. So this is us adding heat to something. So if you add heat to something, then the temperature is going to increase. And so over here is going to be the temperature. So you can say that's the temperature in Celsius, and this is the heat in, let's say calorie. And let's say here we're talking about water. So let me just draw it out and then explain. So if we have water, or actually a water that's at a very, very low temperature, it's going to be ice, right? So you could think of this region here. That region right here is ice. So this region right here is ice, so you can kind of think of this right here being 0 degrees Celsius, because once you're below 0 degrees Celsius, you basically have ice, right? And so right at 0 degrees Celsius, we have this state of a ice water mixture. So this is water and ice. And so once the water or all of the ice becomes water, then kind of continue on. It's just a little too high. I'm gonna go right there. This is just water. So from here going up here, this is basically us heating it up, and it's still water. So at this point, you can imagine that being 100 degrees Celsius. And so at 100 degrees Celsius, it's going to begin to steam. Then this would here would be water and steam. Then it's going to increase, and then all that after here is just steam. Boom. So basically what I want you to see here is basically when it's below 0, we have ice here. Then we add some heat. So we go to the right, adding heat, increases the temperature. This ice gets to 0 degrees. Now it's starting to melt. So once for this region, we have to add a certain amount of heat. For this ice to melt and become water. And so at this point, it's all water now. And now we can heat it up, and then this water just heats up until it gets to 100 degrees Celsius. Then once it reaches 100 degrees Celsius, the water begins to evaporate. And now we have a mix of water and steam. So now in order for that water or all that water to become all steam, we have to add a lot more heat before it can become steam. So basically all this just to show you that the amount of heat required, or the amount of heat required to go from water and steam to steam is a whole lot. So let's put some numbers to it. This is 200 calories. And then to make it all steam, you have to go up to 470 calories. Whereas to heat up this water, it's only 100 to 200. And from here, or from ice to water, it's only 20 to 100. So that's kind of why I have this break here, because it's actually a lot longer than this, because it goes from 200 to 740. So a lot of heat is required to turn all the water into steam. A lot of heat is also required to turn water or ice into water, but not as much from water to steam. So I hope that makes sense. Okay, it's looking at the slides here. All right, so I think that's just about it as far as the slides go. I guess the last thing we're going to talk about is boiling, which would be kind of like right here, right at the 100 degrees Celsius. Boiling. So we got some pot here. It has some water. And here's our flame. So we know boiling basically begins to happen at 100 degrees Celsius, right? So boiling begins to happen at 100 degrees Celsius. So basically the water on the bottom of this pot here is actually what's beginning to boil. And so once it begins to boil or gets enough energy, it actually makes a air bubble. And then that air bubble is going to float up to the top and be released through the top. And then as that is released through the top, as it's released to the top, it actually cools the liquid because energy is being lost. But because this water is constantly under this flame here, the temperature basically continues to increase, even though boiling actually causes the water to cool. All right. So now I kind of want to talk about two problems in the Mastering Physics homework. I think they're like two of the last problems. So here's one of them. In the Mastering Physics, it says a 70-gram chunk of 90 degrees Celsius iron is dropped into a cavity. Dropped into a cavity in a very large block of ice at 0 degrees Celsius. What is the mass of ice that melts? What is the mass of ice that melts? Okay. So first, let me kind of draw out the picture here. I'm guessing it's something like this. We have something like that. This is basically ice. That's ice. And we dropped in a 70-gram chunk of iron. I'll make it a square so it's the perfect size. Drop that in there. This is iron. You can see that this is iron. So this is iron at 90 degrees Celsius, and this is ice at 0 degrees Celsius. Boom. So we know basically once you put this iron into the ice is going to begin to melt, right? Because the heat from the iron is going to be transferred over to the ice. And so there's another equation for heat that I did not discuss yet, but let me see if I can describe it here. Just keep this picture here in mind. I'm gonna draw it again. So we know there was the equation Q equals, or Q being for heat, equals MC delta T, right? So this is for if we add some heat to an object, this is how much the temperature is going to change. Okay, now let me show you kind of where that applies. Boom. So remember, this is the heat temperature graph that I drew a moment ago for water. All right, where this is heat on the bottom, this is temperature going upwards. And so right here, now that's ice. This is water and ice. This is water being heated up. And then this is water and steam, and then steam after that. So basically this Q applies to the positions where the temperature is increasing, because you see there's a delta T here, where there's a change in temperature. And so for there to be a change in temperature, there must be an incline in the T, right? So this Q applies to each one of those moments. So here where the ice is increasing in temperature, or here when the water is being increasing the temperature, or here when the steam is increasing the temperature. It's in between here where the phases actually change. So let me put that in red. Boom. So here would be fusion, right? This is fusion. Because from what I said earlier, fusion, or from what I said earlier, right? Fusion is when you go from solid to a liquid. So from here, we're going from a solid, which is ice, to a liquid, which is water. So this region here accounts for fusion. And then this region here, we're going from a liquid to a gas. So that's going to account for evaporation. So this here is evaporation. I'm shorthanded, evaporation. So how do I get the basically heat needed for fusion, or Q, the heat needed for evaporation? Well, that Q is given by Q equals the mass times L, where this L is for either fusion or evaporation. We call it latent heat of fusion or latent heat of evaporation. So basically, if we have some mass of ice, right, and we want to melt that ice, we want to melt this ice, so we need fusion. This equation here would tell us how much heat we need to completely melt the ice. So whenever there's a change in phase, this is the equation that we use. Whenever we're just changing the temperature of that phase, so if we're just increasing the temperature of some water, then we use this Q. But if we want to, boil water, and we want to know how much, heat that we need to completely boil some water, well, that's basically a phase change, right? So that's a phase change. So we use this Q, where this gives us the amount of heat needed to boil a certain amount of mass of water completely into a gas. Because here, this is basically a mix of gas and water, just how here in fusion, this is a mix of water and ice. All right. So boom, this is, I think, the one equation you need to keep in mind for basically this chapter. So now let me use that in that problem. So now going back to the problem, which said, got the 70-gram chunk of iron, and we dropped that into some ice. And I'm asking what is the mass of the ice that melts? So let me draw it again. All right. So, if we first are to think about I think it's one of the laws of thermodynamics that says energy cannot be created nor destroyed, right? So basically energy is conserved here, or we can say the heat is conserved, because heat, or Q, is a form of energy, right? So we can say the Q loss is equal to the Q gained. Boom. So this would be for the ice, right? Because the ice is going to gain some heat from the Q, or from the iron. And then the iron is also going to lose some heat because, the heat's going to transfer from the iron to the ice. So let me write this in red. So the Q loss is equal to the Q gained. And so basically the same amount of heat that the iron is going to lose is going to be the same amount of heat that the ice gains. Now, since this ice is melting, or basically it's changing phase because of this iron, for this ice, we're going to use the equation ml, where this is the mass, or how much the mass of the ice that's going to be melted, times L, where this L is going to be the latent heat of fusion for the ice, which is given by 80 calories per gram. So this is, I'm gonna write a little F there for fusion. So this is the latent heat of fusion for ice. So that's gonna be equal to, the heat loss by the iron. And so for that, we're gonna use the other heat equation, which is just gonna be mass. So mass of the iron times C, which is the specific heat of the iron, times T. Yeah, times T, which is going to be the temperature of the iron. So this is for mass of the iron, and then this M is for the ice. Boom. So now we can actually solve for how much ice is going to be melted, because we know what this L is. So now we can solve for what that mass M for the ice is going to be. Well, that's going to be mass of the ice is going to be equal to all this, right, divided by L. So MCT divided by L. So again, that M is for the mass of the iron, which was, I don't remember what it was, but it was given in the question. So whatever the mass of the iron was, times the specific heat of the iron, which I think was also given in the question, times the temperature of the iron, which was 90 degrees, I think. So T equals 90 degrees Celsius. Then all that divided by 80, which is the latent heat of fusion for ice. Then that's going to give you the mass of the ice that is melted. All right, so I hope now when you get to that in your mastering physics that this problem makes a little bit more sense. And then there's one more I want to go over. And then that's going to be it for this video. So the next mastering physics problem is a 15 kilogram iron ball is dropped onto a pavement from a height of 150 meters. Suppose that half of the heat generated goes into warming the ball. What is the temperature increase? Okay, so first let me kind of describe what's happening here. We have a ball being dropped from a height. Boom. So we have a ball basically being dropped from this height onto the ground. So I think a few weeks ago we talked about energy, right, and conservation of energy. And so how, because this ball is at some height, it has some potential energy, right? Well, if this were a conservative system, meaning no energy is being lost, the ball would actually fall down, hit the ground, and bounce back up to this exact same height, right? If there was no energy loss. But in this case, well, in the actual real world, energy will be lost. So the ball will fall down, hit the ground, and bounce back up, but it won't go as high, right? It'll probably hit the ground, go back up, and reach some height like that. Go back down, hit the ground, probably reach some height like this. So basically, as the ball bounces, it's losing energy. And basically that energy loss in the ball is being lost in the form of heat. And so as this ball loses energy, it's losing energy in the form of heat. And so as this ball basically bounces, it's actually getting hotter or transferring heat into the pavement, or into the ball, I mean. Cool. So hope that makes sense. So that's basically the scenario that they're talking about here. So this ball being dropped from some height, and then half of the heat generated is going into the ball. So let's see how we can solve that. So first, let's write out our heat equation. And we're gonna use this one, delta T. All right, so this is gonna be the heat generated, the mass, specific heat, and the change in temperature. All right, so we're trying to find that change in temperature. So let me rewrite this equation this way, divided by MC. And so the question says, suppose half of the heat generated goes into warming the ball. So another way we can look at this, we could say half of the energy generated goes into warming the ball. So half of the energy generated from the ball being dropped up here goes into heating it up. Well, how much energy does the ball have when it's dropped from this height H? Well, since we know it's up here some height, it has some potential energy. So up here it has some potential energy, right? Given by mass times gravity times H. So basically what they're saying is half of this energy generated from the ball being dropped at this height is going to be transferred into temperature. It's basically going to increase the temperature of the ball. So since Q, or heat, is a form of energy, and potential energy is also a form of energy, we can actually rewrite Q as mgh. All right, but it says only half of that energy is going to be transferred into heat. So we can actually cut that in half. So half of this potential energy, half of the potential energy is going to be generated into heat, changing the temperature of the ball. So now we can solve for the temperature here. Well, it's a mass on the top. Both of those can cancel out. And so now, let me rewrite it over here. We have delta T equals 1/2 of G times H divided by C. So we have the acceleration due to gravity times the height, or how high you dropped it from. Cut that in half, and then divide by the specific heat of iron. And that's going to tell you how much, or it's going to tell you the temperature change in the iron after it's dropped. So after you drop it from some height, the ball is going to be a little bit higher, or a little bit hotter, I mean. And then that's going to be given by this change in temperature here. And then also notice that this has no value of mass in it. So the change in temperature does not depend on mass, so it doesn't depend on mass. So it's just a small note. So notice it doesn't depend on mass. It doesn't depend on mass, but notice that it does depend on the height. So the higher you drop it from, or the higher the H is, the higher the change in temperature, or the increase in temperature, is going to be for that ball. So the height from which you drop it does matter. The mass of it does not matter. All right. So once you get to that question on your master in physics, I hope that makes a little bit more sense now. That's about it for this video. I hope y'all enjoyed it, and yeah, good luck. See you next time.